And howdy Calculus 3 students, we are doing section 15.2 today, covering line integrals. Here we have a definition of a line integral, so this is going to be what our line integral is equal to. And we are to find the average temperature of a circular plate with the given boundary, and the temperature function is given here. So this would be our F, and we're to find that average temperature. Our line integral is going to be just the integral from, and this line integral is of the edge of this plate, which is going to be just a regular 0 to 2 pi, and that value of that line integral is 1, and that would be, this is ds. Integrating this, I get just a plain old s, and then so s evaluated from 2 pi to 0, so I get 2 pi for this line integral. I know that my average temperature is going to be 1 over 2 pi, which is that line integral. And then I'm going to use my temperature function, which is the 100 times the x squared plus 2y squared. And this needs to be integrated with respect to s. This x and y, in terms of s, the x is your cosine s and the y is your sine s, so let me substitute those. 1 over 2 pi. Oops, I better put my limits of integration on here. This is again from 0 to 2 pi because it goes all the way around. And this would be 100, and then I've got cosine squared s plus 2 sine squared s ds. I'm going to then integrate this and see what we get. Here's a cool little trick here. I just busted apart this 2 sine squared s, and I note that this is a 1. That'll allow me to integrate this very nicely, and I will get that this is 100 over 2 pi. Completing this integral, you will then get that to be 3 pi, so times 3 pi. Doing this, performing your little computation, you will get that this equals then 150. That's the average temperature on the edge of the plate. In our next example, we still have our circular plate, but this time our circle has a parametric description, and there it is. Given this procedure along with our theorem, what I will need to do is find the magnitude of my r vector, and that is just going to be this x prime of t quantity squared plus y prime of t squared. Taking those derivatives and squaring them, you will get, I'll do this algebra. There's what we get for our magnitude. Now let's do our average temperature. Our average temperature is going to be 1 over, and that is our length, and we got that in the previous example, so I'm just going to write this as 1 over 2 pi. And this is our new stuff. We're going to be integrating this in this format. That means my limits of integration, noting that my t goes from 0 to square root of 2 pi, and then I will have 100 and then x of t squared plus 2y of t squared times the magnitude of my derivative of my r vector, and then dt. Plugging what I have in for this, let's do that and then integrate. Alright, after plugging all of this in, I will note that this right here if I let u be my t squared, I have a du sitting right there. So I'm going to do that u substitution where let u equal t squared. Then that means I have du equals 2t dt. I'll do that substitution and then integrate. Computing that integral, then you once again get 150, which was what we expected. Alright, we're going to do this in 3 space now, and first up I have to write the parametric description of the line from P to Q. This is taking me back a little bit. R of t is going to be, choose my starting point here, and then I need for it to be, how do I get to this point Q, which is 0 there, so this would be a -1. Oops, I need a t here. And then how do I get to 1? Oh, then that would just be a 1, and likewise for that j component. That means that this r of t is then equal to 1 minus t, and then it is just t, just combining that, and that is from t going from 0 to 1. So I'll just go ahead and put the restrictions here on t. Now I need to find the magnitude of r prime, so I will find the derivatives, quantity squared. So this is -1 quantity squared plus 1 squared plus 1 squared. This then gives square root of 3. Now we know this is our x, this is our y, and this is our z. What they have us do here is I need, in order to evaluate this, I'm going to do this x, y plus 2z integrated with respect to s. This is going to give me, I'm going from 0 to 1. I'm going to write my x component, which is 1 minus t, multiplied by my y component, which is just t. I'm just going from this here. Then I'm going to say plus 2 times the z component, and the z component is just a t. And this is all times the magnitude of that derivative of my r, which is square root of 3 dt. And then I will integrate this, and when you integrate this guy right here, you will end up with 7 square root of 3 over 6. And in the b part, we're going to do the same thing again. So let's find that our r of t, and going from one point to the other, and we're going to do the same thing but in a different order, and we should get our same answer. So let's see if we get that. Alright, there's the setup, and when you integrate that, you will get the same as what you got for the alternate order. In our next example, we are to find the distance traveled by this eagle, and the length then would be equal to the integral there with respect to s. For this is our r vector here, so we're going to need that magnitude of that vector, its derivative, and that would be, now I'm going to take the derivative of each of these components and square them and place them in there. Alright, just using a little trig there with your sine squared plus cosine squared is 1. We'll end up with this magnitude here. That means our line vector is now integral of, from 0 to 10, of the magnitude of our r vector, which is 1300, and then dt. And for this, you then get 13,000 feet when you integrate that. Alright, first up we have our definition of a line integral of a vector field, and here is the integral that we'll be working with to get that line integral of a vector field. We will use our unit tangent vector at each point C. here are some different forms of those line integrals, and we will use whichever is most appropriate for our situation. In our A question here, we are to do the quarter circle from this point 0, 1 to the point 1, 0. So we're going to go clockwise in this fashion. This would mean that our R vector for A is then going to be the sine of t for our first component, and then the cosine of t for our second component at any point along the curve. This yields our f vector to be, since it's y minus x, I would say that this is cosine t minus sine t, and then the second component is just the x, which is then sine t. What I need to do next is the dot product of my f vector times the derivative of this r, or dot product, sorry. So here's my f, and my f is the cosine t minus sine t, comma sine t. I need to dot product that with taking the derivative here. This would be cosine t minus sine t, and in doing the dot product of those, you will get cosine squared t minus sine squared t minus sine t, cosine t. Alright, that is stunning. I could write this a little simpler using some trig identities and just say that this part right here is cosine 2t minus, and I could write this thing as 1/2 sine 2t. That will make it a little easier to integrate. Now I'm to do the integral of this thing from 0 to, and this is pi over 2 because I'm on the quarter circle, and it is my f vector times dot product this derivative of my r vector, and I'm going to integrate that and see what we get. So for our a portion here, we get -1/2. So this is our a portion. Now the b portion just asks us to go the other direction from q to p, and for this one you'll just get the same thing but in the other direction. So we can do the integral again, but we will get +1/2. In the c portion, we're supposed to go from p to q in this fashion here, and so I need my r1, and my r1 vector is going to be going from the p to the origin. It's just going to be 0 and then 1 minus t, where t is varying between 0 and 1. And then r2 is going to be t 0, and the next thing that I'll need to do is then I'm going to do this in 2 separate segments, so that means I'll have 2 separate integrals. So in order to get this total integral, I'm going to do this f dot product unit vector with respect to s. So I'll do the first section. The first section is going to be that f. Oops, I need to see that f. That is the y minus the x. So the y minus the x is going to be 1 minus t, comma 0, and then just the x component was just 0. Dot product with, and the derivative of that r vector is just 0, -1 dt, evaluated from 0 to 1, plus integral 0 to 1 again. Now I need this f vector, and it's going to be y minus x on this r2, so y minus x, so that would be a -t, and then just the x is just a t. Dot product with the derivative there, which would just be 1, 0 dt. Evaluating this integral, you will end up with negative 1/2, which would be expected because it's what we got on the a part going from p to q. We can now apply what we just learned to work integrals and get the work done in a force field. In example 6, we're going to do just that. So first up, we will need to get our r vectors. Right, in writing this in terms of t, notice that t is going to be going from 1 to some a value. My r vector in this case is just going to be t, 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 and that means that my derivative of my r vector, and well, not, yeah, the derivative is just 1, 1, 1, so then if I need that magnitude, which I don't need right now on this one, sorry about that, I just need to find the vector itself. Okay, I don't know that my video is running. I don't think it was, so I'll just kind of run through this pretty quick again. My t is going to vary between 1 and a. That means my r vector is just all t's for each one. The derivative of this is just 1. Putting this in terms of t for my f, my force vector, that is just I just substitute in here for each of those a t. Now I'm going to get this dot product. So when we substitute and get that dot product, we can now say that the work for this is going to be equal to, from 1 to a, our starting to ending point, of k cube root of 3, and that's going to be t to the minus 2 dt. That way I can integrate it a little easier. Notice that that is down here in the bottom, and after integrating that you will get k over square root of 3 and 1 minus 1 over a. So that would be our final answer for our a portion. For the b portion, what we're going to do is let a go to infinity, so I just need to take this work. It's going to be the limit as a goes to infinity of my k over the square root of 3, 1 minus 1 over a. I like this integral. This one's pretty nice. I mean, this limit, this is pretty nice. This is just k over square root 3. All done with that. Next, we're defining circulation. It's a very similar integral that we are going to be dealing with here. We're going to need to find the C is our unit circle, and we're going to be going in the counterclockwise direction, so we're going to find the circulation for C on this particular vector field. This would yield that our r vector is cosine t, sine t, since we are traveling in that counterclockwise direction, and note that t is going to be going from 0 to 2 pi. So what we are going to do is we're going to compute our integral here. So let's write it down. F dot product our t ds, and let's see what we can plop down on in here. So what we're going to get is this goes from 0 to 2 pi. Our f vector is just an xy, so this is going to be our cosine t sine t dot product with, I need the derivative of my r vector, so I'm going to get negative sine t and then cosine t dt. Computing this integral, you should get the integral of 0 to 2 pi. Doing your trig, doing your manipulation there with your algebra and your dot product, you're going to get that this is 0 dt, and so I get this guy is equal to 0. Pretty nice. This tells us that the tangential component of the radial vector field is 0, everywhere on C, so the circulation is 0. On B, the rotation field is negative yx. Very similar to what we just did. We have our same r vector, but our f changes this just a little bit, so let's write down what we're doing. I'll write down that integral, and just doing my substitution here, I get this is going to be a 1, take the integral of that, you're going to end up with 2 pi. So in this case, at every point C, the vector field is in the direction of the tangent vector, and that means we have a positive circulation. In this case, they have given us our F, they've given us our R. We are to find this circulation with our F dot product with our T unit vector here. And what we're going to get when we substitute this in, this is going from 0 to 2 pi, substituting in our variables in terms of t. We've got cosine t, minus sine t for the y, the minus y, dot product, and in this it's just the derivative of my r, and I'll write this algebra down. Alright, and doing that dot product and then just combining a little bit, I get this, and computing this integral, I will get 2 pi. All finished with this one. Very similar to what we have been doing, we are defining flux to be this this force vector and this field dot product with the normal, the unit normal vector, and we're going to define it to be this. So this is our flux, and we are to find the outward flux in the counterclockwise direction. That gives us that our r vector is then the cosine t sine t, and this is for the x and this is for the y of t, so that way I can plug in for each of my derivatives there. Also notice that t in this case goes from 0 to 2 pi. In writing down my integral, I am going to get that this goes from 0 to 2 pi. I will need to multiply my function, which is in this one is going to be cosine t for the f, times the derivative of my y. So the derivative of my y is cosine t, and then that's going to be minus, and I'm going to need my y, which is sine t. It's right there, y times the derivative of my y of t, which is then going to be minus sine t dt. Then this is going to yield the integral of 0 to 2 pi. It's cosine squared plus sine squared, so that's a 1 dt. This thing equals 2 pi. Nice. Alright, because the radial vector field points outward and is aligned with the unit vectors, we have an outward flux that is positive. Next, we're just going to do this with a different f. I'll go ahead and write all this down. Alright, this is my minus y times the derivative of my y term, which is right there, and then minus, then this would be my x term, which is the cosine times the derivative of that x term. So in this case I get 0 for the outward flux. And that concludes section 15.2. This was a long one.